Okay, so 3-1, we're going over the basics of exponential functions. We'll talk here about exponential growth, exponential k, and then we'll move forward with the overall model along with transformations of the graph. So before, I know you've probably seen 2 to the x as well as 1/2 to the x, but we want to get into specifics. So starting out before with anything within mathematics in terms of understanding the behavior and properties of a function, pretty good to start out with an input-output table most times. So let's start out, if we plug in -2, note I'll do this one explicitly. If we plug in -2, we have 2 to the -2, which means we flip the base and turn the exponent positive, so that gives us 2 squared, which is 1/4. So therefore, -2 gives us an output of 1/4. If we plug in -1 and flip it, we get 1/2, so that'd be a half. 2 to the 0 equals 1. Anything to the 0 other than 0 to the 0 always equals 1. We'll talk about that later more in depth if necessary. 2 to the first is 2, and 2 to the second is 4. We go ahead and graph these as accurately as possible. And now we have our exponential growth. If we think about in the negative region, that would just be 1/2 to the third, 1/2 to the fourth, 1/2 to the fifth, and so on, which means it's going to get smaller and smaller, but never reach the y-axis, which means we have a horizontal asymptote at the y-axis. Here's our basic model. The key point that we're going to use for our transformations is the coordinate 0, 1. Because if you have 4 to the 0 or e to the 0, we'll get into e later, that will always equal 1. Domain for this is all real numbers, which can be indicated by you can take a base of 2, or a base of 2, 3, etc. Note up here, in order for it to be an exponential function, a has to be greater than 0. Coefficient from b, in this case is 1. 1 times 2 to the x. b cannot equal 0, the scalar. We'll talk about that term scalar if necessary moving forward. If we look at the range of this, going from down to up, our range would be 0, not including 0 to infinity. X-intercept, we don't have any. Y-intercept, our y-intercept as we talked about is 0, 1. It is increasing for the whole graph. So increasing on the interval of -infinity to infinity. Horizontal asymptote at y equals 0, and no vertical asymptote. We'll talk more about why the vertical asymptote will come into play when we get into logarithms. All right, let's check this out. So if we plug in -2 into that, I'll go ahead and do this first one explicitly. So if we have -2, now that flips the base to 2/1. And turns the exponent positive, so 2 squared will give us 4. Then 1/2 to the -1, flip that, will give us 2 to the first, or 2. 1/2 to the 0 will give us 1. 1/2 to the first gives us 1/2. And then 1/2 to the second gives us 1/4. So it's inverting the outputs relative to the first function. We go ahead and graph those. -2, 4. -1, 2. 0, 1. 1, 1/2. 2, 1/4, and we see now exponential decay, where the first one is considered exponential growth, and we still have our horizontal asymptote. Y equals 0. Domain would be the same, -infinity to infinity. Range would be the same, 0 to infinity. Still no x-intercept. Y-intercept, still 0, 1. So whether we have exponential growth or decay, we still have the same y-intercept, or same key point. Increasing, decreasing, now it's decreasing on the interval of -infinity to infinity. Note revision to that up there, that's supposed to mean it's increasing. Horizontal asymptotes at y equals 0, and then vertical asymptote is none. So those are our basic models. We see that, I think it's on the next page actually, as far as generalizing it. Okay, so that's what we see here. For a is greater than 1, that's going to be exponential growth. So we'll call that exponential growth, since it's growing over time, as if we think of the x-axis of time. And if it's between 0 and 1, then it's exponential decay, as we saw with the 1/2. because that fractional base will flip the exponent and therefore reflecting the y values or reflecting the x values to get the same y output. Hence reflection over the y-axis. Now, moving on to this thing called E. E is a natural occurring number, which we'll talk about why it's naturally occurring within exponential growth, 2.718. If you just remember 2.7, that's good enough. Just kind of like pi is 3.14. These are fundamental constants, not like our notation of 1, 2, 3, and so on. Those are units that are feet or meters. Those are units that humans created for us to better understand physicality as well as time. A second is not some standard natural unit occurring within nature. E is, and we'll talk about that. So if we look at a graph of, I'm supposed to do, so if we're just coming back up to above, if we're sketching a graph, right, we're not doing an input-output table. What if I say sketch a graph? What are the important aspects of that? First aspect is having the correct key point, which is in this case is 0, 1. Second, the general behavior of exponential growth, which would look like that, flat, essentially flat increasing and then exponentially increasing or very fast increase as we move up. In terms of that rate of change, that's something you talk about in calculus. But that's the second part. And then the third part is a horizontal asymptote. Those are the three key features of sketching a graph. For this, 0, 1 is your key point, but then exponential decay, you want a graph that looks something like that. And then again, the horizontal asymptote. Those three things, the key point, exponential growth or decay, and the horizontal asymptote, when asked to sketch a graph, are the three key components. Okay, so if we look at a graph of e to the x, you could just look at it on like Desmos calculator or your TI-84 or whatever. You'll see that the graph of 2 to the x and e to the x look virtually the same. Same with 4 to the x and so on. Anything over 1, you're going to have exponential decay. So ultimately, graph key point is going to be the same. Growth versus decay. If it's a growth problem, it's going to look the same essentially. If it's a decay problem, whether the base is 2 or the base is e, is going to be the same. Only difference is the rate. The e to the x will grow just a tiny bit faster. So all that being said, now if we want to translate function, we just use our transformation rules on this, just like we do our other parent functions. So right here, this is a +1 on the inside, so Spider-Man rules tell us it moves left 1. Next one, -x, so that's opposite input. So think about moving, like if here's our xy axis, that means positive x values go to negative. That's a reflection about the y-axis. So reflect over y-axis. I'll just put ya. Here we have multiple things happening. First thing is we have the +2, so that would, since it happens to x first, so we first move left 2. Then we have the negative on the outside, which is a reflection about the x-axis, as y's would go from up to down. So it's reflect over the x-axis. And then lastly, we have a +1 so, on the outside. It's written first, but it's still the same as +1 after. So that's just kind of written in that order, as it's nicer to have a positive term first and the negative term second, but still like a +1 after it. I kind of went out of order there, sorry. This one right here is negative on the outside, so that moves our y's from up to down, so that's a reflection about the x-axis, or a reflection about the x-axis. And then lastly right here, a +1 would be an up 1. Let's see what happens when we have a 3 out front. So if I plug in -2, that would be 1/2 for the first part, but then we multiply that by 3. So it'd be 3 over 2 or 1.5. If I plug -1 in, that would give us 1/2. Did I do that incorrectly? Yeah, I did. Let's go back on that. So if I plug in -2, that would be -2. 2 to the -2 would be 1/4, just like from before. And then we have it times 3, so that'd be 3/4. So it'd be 3/2. Plug in 0, that would be 2 to the 0, which equals 1, and then 1 times 3 is 3. So look at that, that changes the key point. Let's see how that plays into it. 1, we have 2 to the first is 2, 2 times 3 is 6, and then 2 squared would be 4, 4 times 3 is 12. So let's go ahead and try graphing this. We have negative 2 3/4, about right there. Negative 1, 1.5, about right there. Kind of hard to do with the stylus getting this accurate. 0, 3. 1, 6 off the graph, and then 2 12 is off the graph. So you still have this exponential, and our we would still get really, really close to 0. That didn't shift that at all. Now, if we take all of those and do a -1, that's not expanding the graph at all. That's simply dropping the graph 1, the previous graph of what we just had. So instead, we now have this asymptote down here, our 0, 2 3/4, negative 2 3/4 now goes to negative 2 1/4 because it's 1 less. Negative 1, 1.5 will now become 0.5. 6 down 1 would be 5, and actually graph that, we're still going, whoops, I forgot the 1. 1 would be 5. 1 would be 5, not 2. That looks better. Output for 1 would be 5. Right, because before it was, 6? Yeah. Awesome. Okay, so what does that tell us? Let's see. So in general, we're going to call this coefficient of the exponential term b. A is our base, minus c is what we subtract, and plus d. So let's see if we can come up with something here. Well, this 3, with this one, we have a b value of 3. Actually, let's start off with a. So a first. What does a do? A is the base, and that tells us whether it's exponential growth or decay. And if you want to write more info in here in terms of growth being greater or than 1, then it's growth, and between 0 and 1, it's decay. B, note if B is plus minus, that will reflect the graph regarding the output, so the x-axis. So if B is negative, it would reflect about the x-axis. If B is positive, it stays the way it is. I'm just going to put a slash here because that's not it. Now, C, let's go to C and then come back to B and then finish up D as well, as B and D are related. So C is the transformation about X, which means move left to right. So this would be left-right movement, left-right translation. Based on Spider-Man rules. Okay, so let's take a look at this now. Let's evaluate this. So here we have 3, and our key point is 0, 3. That's what I'm focusing on. What does this 3 do in terms of figuring out our key point without us having to do an input-output table? And we'll practice that in a little bit. So we see it's 3 here. Now here our b value is 3, but it isn't 3 here. But if you notice, there's similarities that didn't change between the key point and its distance from the asymptote, whether we had a -1 or a +0. Here our distance was 3. Here our distance was 3. When this is 1, our distance is 1. So what B tells us is more importantly than just a reflection. So B equals the distance from the horizontal asymptote and what we're calling the key point. The key point that we transform whenever we're given a function and we want to sketch it, rather than having to do an input-output table. And then D is where the horizontal asymptote. So D equals where our value of our horizontal asymptote. So horizontal asymptote will be y equals D. That being said, let's see if we can graph the key point, horizontal asymptote, and then sketch. So first off, A, I'm going to erase this, going out of order here. Let's go in order. A equals E, which is greater than 1, therefore, and you don't have to write this out when you do this, I'm just doing this for note-taking purposes. This would be exponential growth. B equals 2, so our distance from the asymptote to the key point is 2. C is 0, so no horizontal shift. D equals 3. So we're going to start out with the horizontal asymptote at 3. And then our distance for B is positive 2, so it's 2 from the 3. Now is that 3 going to, or the 2 is our key point, its distance from the asymptote 3 going to be 2 up or 2 down? Well, B is positive, which means there is no reflection, so therefore is going to be up. We have shifted the whole graph up and expanded it, but we haven't reflected it because B is positive. So we still go up. Now, if that was a negative 2, then we would go, instead of going from here up 2, we would go here down 2, but B is positive. So we also have E is greater than 1, so we have exponential growth. So therefore, we start here and then sketch up. Lastly, of one-to-one property for solving equations, let's look, if we have 2 to the x equals 2 to the third, that's fairly straightforward that those exponents are going to be equal. So one-to-one property says, therefore, if bases are equal, then exponents are equal. And this gives us a very, very easy way of solving not all, but some. And note, this is what's called biconditional, where if exponents are equal, then bases are equal as well. So that tells us, like with our example here for number 6, that if we get like bases, then we can set the exponents equal. So right here I have a base of 2. I'm just going to put it in parentheses to make it a little more clear. And then we look at 32. We know 32 is 2 to the 5th. Well, that's 1 over 2 to the 5th, so we don't have like bases yet. We have 2 on the left and our base on the right is 1/2. So now we're going to come up here, we're going to flip that. One on the right hand side, so I could have flipped the one on the left hand side, but I think it's easier to flip 1 over 2 to the 5th, 2 to the negative 5th. Now we have like bases, so our exponents are equal. Add over 2, x equals negative 3. Basic model. I can't remember if there's these problems in your homework tonight. Might be, and we're going to work a significant amount more on this as we move forward, but the basic compound interest per unit time. Say you have a savings account with initial amount and a rate, and it's compounded every month over like a yearly rate. That's your basic model, where A is our ending amount, P is our initial amount, R is the rate, like 4% per year. N is the number of times it's compounded, so if it's yearly, or I'm sorry, if it's monthly, N is 12, if it's yearly, N is 1, and then time is for how many units of time, like if it's years, how many years do we do it for. If it's a continuous model, meaning this is continuous growth naturally occurring, or it's not calculated at specific times, then the model is PE, as in the base of E to the KT, or PERT. K or R are both variables acceptable use for the rate, radioactive decay, and many other problems. And for those examples, to help you with those, just go to 224, 225 in your book. Example 8 and 9 gives you those basics on that, and we can look more at that in class, and we're going to spend a good amount of time at the end of the unit working on those.